Okay, here's the second video about number representation. Y cómo convertir. Did I just say words in Spanish? Now everybody's freaking out, right? Because you thought, oh, I'm getting a lesson in a foreign language. Number representation. So, in the earlier video I posted on Moodle, I show sort of like a pattern how to convert from any system to decimal. So now I want to show you how to convert sort of a different strategy for converting decimal into binary, for instance. So first of all, we need to recall those concepts from high school. We have the dividend, right? We have a number which is, let's say, in decimal, 5, and we have a divisor, which in this case will be the number in which we want to turn this number. And just to be specific, so if you're dealing with mixing in an example between systems, it's wise to place the base right next in subscript small number of the base of the system you're dealing with. So that's a 5 in base 10, and this would be 2 base 2, that is the binary, correct? Now the way you want to do this is to produce remainders and quotients. So this guy is called dividend, and dividend, is that right? Dividend and divisor. Okay, and now what you want is to divide this number 5 by 2, but you want to have a quotient and a remainder. So what's the way we can divide this 5 is by doing the following. So you will do what number divides 5 so that it's not it divides evenly. That would be the number 2. Okay, with remainder of 1. How do I know that? Because, I'm sorry, this is 10. That is because if you multiply 2 times 2, right, these two guys, it gives you 4 plus that 1 here, add up to 5. All right, so that's why you know that this operation was correct. So now what you do is just put another 2, which is the base. You keep the base next to these numbers, so we know what we're doing. Now you want to multiply, for instance, how many ways you can divide 2 so that you have a quotient, right? So we say that everything that is in this box, right, it's called quotient, if I recall correctly. So there you go. Now we want another 2, right? So we want to divide by 2. Why? Because then that is the quotient that you get. 2 divided by 2 gives you 1. And sort of once you mechanize this, you don't have to use the subscript, but in the meantime we'll do. And your remainder, it's 0, correct? So that is because this one times this quotient times the divisor gives you the dividend. Okay? What does all this have to do with conversion? Well, guess what? At this point, your quotient is smaller than the divisor. So even if you put 2 here, you can't really divide coherently without getting integers, right? So here's where the operation stops. And now we're collecting our result. All right, so the way you collect result will be take the last quotient that is smaller than the divisor, that is this part 1, and collect the all these remainders in this order. So sort of like following this direction. And concatenate those numbers. So this is the representation of a binary number of the number 5 in decimal. All right. And how do we know that? Well, you can always prove, right? There's proof that this number is 5 in the decimal system. Well, we can use the polynomial operation we did last time, correct? That is using base 2 times the digit times the digit times the digit, and you add up those and use the exponent for the base based on the position from right to left, starting at 0. Right, 0, 1, 2. So you place a 0, 1, and 2 on top of these, and these are the exponents of this base. And as before, we know that anything multiplied by 0 is 0, and we end up with just 1 times 2 to the power of 2 is 4. 4 times 1 is 4, plus 0 plus 2 to the power of 0 is 1. So this is 1. And the result of this addition, it's 5, right? So that actually tells you that your original conversion was correct. Now you might think, like, what about if you want to convert from other systems? Well, so sorry about that. So here you would do is the following. For instance, if you want to transform between base 10 and octal, well, you sort of repeat the same pattern, but this is just from tens to any other base, right? That would be, let's put a number that kind of fits here, right? This is 10, And then you would use 8 here, and you keep a table for all your reminders and all that. So now what is that you do here is what number you use to divide evenly 16. Well, it's just 2. All right, and remainder is 0, correct? You let's see. Okay, so now you bring down 8, and at this point your quotient is smaller than your divisor, correct? So you stop there. We collect starting here. This is the first number and the second one. So this 20 is your both together concatenated. It's your octal number that represent 16 in decimal. Let's prove that. Let's see if it doesn't make sense. Let's use the polynomial again. And I guess I should clarify that octal system, it's a system which digits, just like the decimal, that the decimal system, right, represent numbers with the digits from 0 to 9. Octal system represent numbers from 0 to 7, using digits from 0 to 7. Binary, as you already know, use numbers from 0 to 1, and hexadecimal use numbers from 0 to 15. However, hexadecimal rather than representing the numbers 10, 11, 12, 13, 14, 15 with actual numbers, it uses letters of the alphabet. So things that start at 10 to 15 will be actually letters from A to F accordingly. All right, so that's just a clarification. All right, so clarifying that octal has numbers that run from 0 to 7, so 2 is a valid digit in the octal system. So let's use the polynomial. So we use the base 8 times 0 plus 8 times 2 and use the index 0, 1. We know this cancels out 0, 0. Any number times 0 is 0, and then 2 times 8 is 16. So there's a conversion. So if you get to see letters in a number, then remember that's hexadecimal. So that makes it for the conversion between two examples from binary to decimal and octal to decimal. You can do the same with hexadecimal. Just divide by 16 and it will do the trick. All right, so that's about it. See you in the next video.